Principles of Building Science series that we're hosting for the Multifamily Upgrade Program funded by PG&E. My name is Mike Maroney, and I'm the Technical Review Manager for the Multifamily Upgrade Program at TRC. Today we're going to be hearing from Scott Blunk, who is the Director of Energy Auditing Services at Partner Energy and a BPI certified proctor. He will be going over, as I said before, the third part of the Principles of Building Science series. We are hosting a series of trainings through the Multifamily Upgrade Program, and the trainings that we've conducted so far have covered a range of technical topics specific to multifamily buildings and how to model specific criteria and scenarios in EnergyPro. And we're hosting a separate series of trainings that this is one part of a six-part series on the Principles of Building Science. At the end of this series of trainings in August, we're hosting a day of field exam and testing to get yourself some experience with hands-on practical applications of using and conducting BPI Principles of Building Science aspects of the program, and also the opportunity to, if you would like to, take the written exam. If you would like to take the field exam, you'll need to contact Partner Energy directly, and they'll work with you on finding a time and a place for you to do that. So the trainings that we've hosted so far have been recorded and are posted on our website with links from multifamilyupgrade.com, as well as through the partner portal, which is available to all partners of the program and provides the documentation for the program, as well as additional links and operations to apply to the program. And these trainings are also hosted on our YouTube page for on-demand viewing at a later date. Final reminder from me is to please, at the end of the training, fill out the survey that we've got configured there for you, and give us some feedback about the presentation topic as well as the presentation materials, and also send us your BPI certification number if you would like continuing education credit for taking this class today. With all that said, feel free to take it away, Scott.
All right, thank you, Mike. Welcome back, everyone. Just to reiterate a little bit about what Mike said, there is a series of EnergyPro technical webinars that are being given. The last one is next Wednesday, the June 24th, and it will be on modeling cooling towers and chillers. The previous versions can be found on the YouTube webpage if you want to find it. And this series is on building Analyst. This is the third, or I guess fourth, in this series. Today, June 17th. Today, HVAC and pressure dynamics, pressure is really going to be covered in the next webinar. At the conclusion of these webinars, there'll be a full day of training, as Mike talked about. It'll be on August 20th. We will do training on testing of combustion equipment, primarily hands-on training. There'll be a review of the material for the written exam, and then the written exam will be given there on site for a cost of $275. Pre-registration is required. We're going to limit that to 30 students, and enrollment will begin next Wednesday. And you can contact Partner to get registered and get your money will hold your spot. We will not be conducting the field exam there, but we will be able to give you a list of resources to take the field exam. And this is the YouTube channel. If you could just simply Google PG&E Multifamily Upgrade Program, it'll take you to the channel, and all the webinars, either the EnergyPro Tech topic or this series, will also be on there. And also, this is an introductory webinar series on BPI for the BPI Analyst training. kind of intended to people who are new to building science and to BPI. If you're not necessarily new to BPI but just haven't been certified yet and you have some experience, building experience or building science, combustion experience, it can serve as an overview to prepare you to take the exams. It's not a traditional building analyst course. The traditional course is usually 5 classroom days in a row, 5 or 6, and at the end of that, then you give your, or you take your 2 exams written in the field. So we're doing it a little bit different this time. Hopefully, it's more conducive to your schedule. All right, so today, mainly we're going to talk about ventilation and cooling systems, and we'll dive right into it. So, for starters, HVAC is heating, ventilation, and air conditioning. They all, heating is also conditioning the air in a way, but air conditioning is, of course, all about cooling. But ventilation is the piece that's often overlooked when we do HVAC, and traditionally it's just been ignored. Now with the last couple rounds of code, ventilation to residential buildings is required by code, and we'll go into that more. So the 3 central functions of heating, ventilation, air conditioning, they're all related. They're primarily, you think of it as to provide thermal comfort, and you also want acceptable indoor air quality, and then you also need to be able to provide 1 and 2 at a reasonable cost and operation and maintenance cost. So the basic premise of HVAC is about meeting the heating and cooling demands of the residents of the home. And that is often dictated by how hot or cold it is outside, of course. And so the severity of a climate is usually characterized in heating degree days and cooling degree days. These aren't talked about as much as they used to be because now we have software that have heating and cooling degree days internalized inside of them. But it is important for the exam to understand that a heating degree day, what that is it takes the average temperature of the day, and say the average temperature is 50 degrees for 1 day. Well, that's 15 degrees less than 65, which is the standard. So that 1 day would have 15 heating degree days. And that's, again, that uses the average temperature. So if the next day, so that day is 50 degrees, the next day it's 40 degrees, so then you'd have 25 heating degree days, and you add those up throughout the year, and that'll give you the severity of the heating climate. And that's directly related to how much heating will be required, how much heat energy will be required in the home. On the flip side of that is cooling degree days, and it works exactly the same way, except it's 78 degrees. So any day that it's above 78 degree days, 78 degrees Fahrenheit, if the average temperature is 90, then that 1 day would have 12 degrees, 12 cooling degree days for that 1 day. And then you add up all the cooling degree days for the year, and that's the total annual cooling degree days required. And you don't, cooling degree days are separate from heating degree days. You calculate the 2 separately. You don't add them together in any way. Cooling degree days is not as good of a predictor of actual cooling energy required for various reasons, but primarily because a lot of the cooling demand that's required is more about the radiant energy from the sun and not about the ambient air temperature. But heating degree days is a good predictor. And being able to do that simple math is important on your written exam. So just knowing 65 degrees is a heating degree day threshold and 78 is cooling degree is important to remember those. Like I said, it's used. These are used in the HVAC design process, although it's all done internal to the modeling software at this time. But it helps you conceptualize the capacity of the system, and capacity, when we say that, we're talking about like how much heat is really required. Do you need a 60,000 BTU furnace or an 80,000 BTU furnace? And then efficiency also plays into that. You might be able to get a 60,000 BTU furnace at 95% efficient, be able to do the same thing that an 80,000 BTU furnace can if it's 80% efficient. Just throwing a couple numbers out there. It's not, but the higher the efficiency, the less capacity you need in the system. And then, 65, 78 are the standards. And cooling degree days is just less useful due to a lot of various reasons. So now we'll go into ventilation. Going to spend a bit of time on it because it's really important to understand. The BPI analyst exam is really all about existing buildings and not new construction. And ventilation is not a part of most older construction, but it should be part of the strategy when you're retrofitting a home. So we'll talk through some of those. Ventilation is the piece that's often overlooked because when you're building a house or working on a house, you never want to spend more money, and of course ventilation it's just an added expense to the install. There's always going to be, any time you install anything, there's maintenance that's going to be required. And in ventilation, it requires energy, so it costs money to run it, and there's no identifiable benefit coming from the ventilation most of the time. Like, you can't say, oh, I'm healthier because the ventilation is in. It's pretty imperceptible, at least when it's working well. And when it's not working well, it can be a constant source of complaints. It can be noisy. It can just be inadequate and not doing what's needed. Ventilation is really important, and it's a big piece of BPI because part of BPI is about sealing the envelope and sealing the ducts and trapping more of the heated and cooled air in the house, and thus saving energy. But when you trap more air in the house, you're also not letting the pollutants that are in the house out of the house. So to make up for tightening the shell while it's energy efficient, it also decreases the indoor air quality. And ventilation is all about the indoor air quality. So from the EPA, the indoor air quality is one of the leading risks to public health. The air inside a home is 2 to 5 times worse than the air outside the home, and people nowadays really tend to try to keep their windows closed and keep that perfect temperature inside the building at all times. And so there's less natural ventilation through windows now for health reasons, safety reasons, trying to keep the windows closed, and of course energy reasons, right? Comfort reasons. But 30% of all buildings do have indoor air quality issues, IAQs, indoor air quality, according to the World Health Organization. There's a lot of things that we take into the home that negatively impact indoor air quality. Cleaning products and mold, chemicals, there's a lot of things that we bring into the home that can adversely affect our health. So poor IAQ, the signs really show up. First, your eye, nose, throat, coughing, headaches, fatigues, rashes, that kind of stuff. Asthma is triggered oftentimes by poor indoor air quality, just more respiratory illnesses. That would be like a cold, pneumonia, that stuff. Is all the risk increases with poor ventilation. It's from indoor air quality issues. And of course, the most vulnerable people to indoor air quality issues are going to be the old and the young, pregnant women, probably won't be pregnant men out there, so and people with existing respiratory issues such as asthma or chemical sensitivities. And there's a lot of substances that cause indoor air quality to be negatively affected. Almost all cleaning products, unless they're the natural products, are going to harm indoor air quality. Basically, if you can smell it, it's probably bad for you. So like laundry detergents that are scented are unhealthy. My favorite is the room air fresheners. The chemicals in those air fresheners, oftentimes they're not designed to make your home smell better. They're designed to make your nose smell less or be less sensitive. So they're not only are they not truly freshening the air, they're covering up the air, and it's really it's designed to make to work on your nose and not the smell. Carpet, vinyl, and adhesives are full of volatile organic compounds, or VOCs, that are bad for you. Carpet also, it traps in dirt and debris, fertilizers and stuff that you're going to be walking in with your shoes. So it traps it in the house and makes it hard to get out of the house. Composite wood, so your cabinets in your kitchen especially, because that's going to be the highest concentration of cabinetry. Lots of VOCs and harmful products in those. They say it takes 7 years to get half of the chemicals to off-gas out of your cabinetry. Paints, of course. California's done a good job of limiting VOC content in a lot of materials, but you can always do more. And programs like Greenpoint Rated and LEED, take it the next step further to get more out of there. Like I said, if you can smell it, it's probably bad for you. Perfume is really 70% of asthma attacks are caused just from perfume. So hairspray, deodorant, dry cleaning fumes, all those are going to be bad for you. And of course also exhaust fumes. When you start your car in your garage, some of that is going to make its way into the house. So all these are reasons why we want good ventilation strategies inside the home, because that's going to, it may not eliminate the source, but it will dilute the concentrations. And then, yeah, this is just a pretty picture of all these things that are harmful to our health and indoor air quality. The range is one there, just cooking is going to be producing carbon monoxide like we spoke of before. But if you can smell it, it's probably bad for you. So when there is an indoor air quality issue, and you know that something is bad, so this is the order in which you want to try to attack that issue. So using the car example in the garage, when you start it up, it's going to be producing carbon monoxide, and some of that's going to leak back into the home. So in order of priority, you want to just get rid of the car. So like a detached garage is better than a garage that's attached, or not to park your car in the garage. But if you can't eliminate the source, you want to try to encapsulate it. And so for your car example, encapsulating it, you can think of it in terms of like sealing the wall between the garage and the house. So make sure the weather stripping from the person door going from the garage to the house is weather stripped well, and then also air sealing all the penetrations from the garage wall into the house. That would be an example of encapsulating. And then your third strategy, if you can't do 1 and 2, or in addition to 1 and 2, would be to dilute it. And so there we're just reducing the harm by lowering the concentration, and that's by diluting it. Really that's just ventilation. Dilution is just ventilation. So the car example in the garage, one way to do that, which LEED likes you to do, you get points for it, would be to put an exhaust fan into the garage. So maybe it's motion activated. Every time somebody walks into the garage, the fan in the garage kicks on and it helps suck out. So it'll create a negative pressure in the garage so that the exhaust doesn't go into the house, but it gets sucked out of the fan. So that would be dilution for ventilation. All right, so why we ventilate, we ventilate to dilute, and that's what ventilation is all about. You also ventilate you spot ventilate to get rid of moisture and smell. So moisture, like from the showers, would be spot ventilation with the shower vent fan, and then your kitchen would be to get rid of smells. I suppose your bathroom would be too. And also it's just the law in California. So ventilation is all about mitigating potential IAQ issues. So I guess we can pause here for a second, Mike, if there's any questions.
I haven't received any questions yet, but I think it's a fine time to just let everybody know that in the GoToMeeting panel or GoToWebinar panel, which is on the right-hand side of your screen, there's a little arrow at the top which is pointing to the right or the left, depending. If you click that, you have more options on what you want to do to interact with us. You can either raise your hand or you can type a question or a comment in chat, and I will be fielding all of the questions both electronically, and Scott will pause periodically to answer any specific questions you have. So feel free to reach out and ask follow-up questions throughout the presentation today, but we haven't had any questions so far, Scott, so go ahead and keep going.
Okay, will do. Yeah, let those questions come in, and we'll handle them as they come in. So, so ventilation methods. There's 4 main methods for ventilation. The first is natural ventilation. So that's like windows. We'll go into each of these in a little more detail. There's spot ventilation, which is typically exhaust only. That's what almost every house would have in their bathroom. Balanced ventilation systems, that's where there's both a supply and an exhaust into a house. And then a heat recovery ventilation system is really a form of a balanced ventilation system. We'll talk more about all of those. The calculation basically stems from ASHRAE 62.2, and there's a chart basically here saying how much air and CFM, that's cubic feet per minute, would need to come in based on the size of the house and the number of bedrooms. And bedrooms is a proxy for the number of people in the house. So passive ventilation is a form of natural ventilation, and that's all about the buoyancy of air that we've previously talked about. Hot air is warm and more buoyant, and it rises out. So most homes wouldn't look like this, but there's some strategy that you could have in the home that allows the hot air to rise up out naturally without any fan moving the air, and it just allows for air to circulate through the building and ventilate. And then there's passive ventilation, and so variations are operable windows, of course. There's louvered vents, so there's the and trickle vents, and the trickle vent is on the window in the top right corner, and then a passive vent is more like the vent on the bottom. Of course, that big tube would be going through a wall, but really all that is an inlet on the outside and an inlet on the inside of the house, and depending on where the pressure is, it would allow air to move through that tube, through the wall, and give you some natural ventilation or passive ventilation. And then, so for passive ventilation, you really want to orient those in an appropriate place. Like in Sacramento, you wouldn't want to have a passive vent on a south or west wall, because it's going to be just bringing in a lot of hot air, where maybe you would if you're in Truckee, where the warmer air from the sun would help the house. So there's a few strategies you can use when using passive ventilation systems. Don't use them very often, but they're out there. And then in spot ventilation, and this is what we see, this is bathroom fans and kitchen exhaust hoods. What you want in them, ideally you're going to have an Energy Star rated fan with a humidistat control. And a humidistat is a moisture sensor, so if you had spot ventilation in your bathroom, it would automatically turn itself on and off according to the level of humidity in the room. Variable speed is also a good option. Smart flow systems is that constant volume, where depending in any ducted system, there's going to be restriction just due to the ducts. So a smart flow system will adjust the fan speed to make up for the pressure in your duct as you take that air out of the house, because sometimes it's going to be, it might be 4 feet long, sometimes it might be 8 feet long. So a good fan is going to adjust for that. And then you also want super quiet operation, not just quiet, but super quiet, apparently. But the reason for that is that what I've found in most homes is that even though they might have exhaust fans, they're not being used because they're too noisy. And I think everyone has done that at some point. The range hood fan or vent is a good example, where they're almost always so loud that you don't want to have it on while you're cooking, because then you can't hear anything else in the house. So if the ventilation, the spot ventilation, is going to be used by the homeowner, it really needs to be quiet enough that it doesn't interfere with them while they're operating in the house. Panasonic Whisper Green fans are definitely my fan of choice when I put these in homes, because they have every one of those things. They're Energy Star. You can buy them with humidistat controls, variable speed, and the smart flow systems, and they're really quiet. And they're just a great fan to use. Of course, they're not the cheapest fan out there, but it's one that will get used after the fact. And so a couple pictures of different fans. These are typically controlled by the occupants, although some fans and the Panasonic Whisper Greens have these where you can set them up to where they're on all the time at a low speed. So you could replace, like in an existing home, you could replace a bath fan with one of these Panasonic Whisper Green fans, And you could set it up to where it runs all the time, 24/7, and is continuously exhausting the air from the bathroom or the laundry room, or any room, but those would be usually where they're going to be installed. But then when somebody goes in to take a shower and wants more ventilation, they can then turn the switch on and it goes to a higher speed. When the switch goes back off, it goes back to its lower speed. Spot ventilation, it's also can be used with the passive vents, so the trickle vents that we showed before, or the vents through the wall. That will help equalize pressure in the house, because these Panasonic fans, because they are on all the time, and when you do flip the switch and turn them to higher speed, they're moving more air. Well, the trickle vents is going to allow for the air to come back into the house. Of course, it's going to come into the house somewhere anyway, but this allows you to determine where that air is coming from instead of just an unknown source of what is it coming from the crawl space, is it coming through the walls. So they can work together quite well. And to give an example, a home that I did, 1,800 square foot home, had 2 of these like smart fans that were on all the time. It was air sealed really well. With both fans on and the house sealed up, the home itself had a negative pressure of about 25 pascals, which is really high. The blower door fan works at 50. So just 2 fans being switched on in a very well sealed home can draw as much as negative 25 pascals, which is a lot, and a good use of a trickle vent there with it to minimize or to decrease that negative pressure. Okay, so balance systems. Balance systems, they exhaust the air out of the home, so you could have an exhaust system in like the bathrooms and laundry rooms. That's where the dirtiest air is going to be found, typically bathrooms, laundry rooms, and kitchens. So you can exhaust air from those rooms, and at the same time you supply air into the house. And typically you're going to supply air, the best strategy, the best design is going to have the supply air going into the bedrooms. So you've got people kind of trapped in their bedroom for hopefully 8 hours a day at least. So you're able to supply the freshest air into those rooms while you're exhausting it out of the rooms with the dirtiest air. So kitchens, baths, laundry rooms. And again, I guess again, also the good thing about having exhaust in those dirtier rooms is you're also creating you're also creating a negative pressure in those rooms, so it's helping to keep those perfumes and hairsprays and stuff inside the room, so it doesn't get outside and drift through the rest of the house. So it's just a really good system to be using, these balance systems. And it's also a great candidate when you have a balance system to do heat recovery ventilators, which are also called HRVs. HRVs, they can be large or small. The smaller residential systems are balance systems. So under the heating mode, or when you're heating the house, the cool air comes in, is being supplied to the house, and the heat energy from the air leaving the house is used to heat the air that's coming into the house. Now the 2 air streams don't mix, so you're not mixing any of the air leaving or coming into the house, but the heat is being transferred from the air leaving the house and going into the air that's coming into the house. So it helps temper that air. So this would say you're in Lake Tahoe and it's 0 degrees outside. Well, that 0 degree air, instead of coming in at 0 degrees, is now being able to come in at maybe 50 degrees or 40 degrees. The efficiency of these are somewhere between 50 and 80%, so you can recover quite a bit of heat through an HRV. And then under cooling mode, it just reverses. So now the air outside is really hot, and the air that you're exhausting is cooler, and the heat is transferred between those air streams, the heat, not the air itself. So it's tempering the air that's coming into the house. So you just use less heating or cooling energy through your HVAC when you have a heat recovery ventilator. And since we're talking about it, an HRV, I'll also mention there's also an ERV, which is called an enthalpy recovery ventilator, or a lot of times it's called an energy recovery ventilator, but it's actually recovering enthalpy, which means that it recovers the heat energy, but it also recovers humidity. This would be more useful in a situation not usually found in California, but let's say Florida, where it's incredibly humid a lot of the time. It could take some of the humidity out of the air before you're supplying it into the house, because a lot of energy from your cooling system is used to dehumidify the house. So if we can get the humidity out of the air before it enters the house, we don't have to spend more cooling energy just to lower the humidity. So ERV is not often used in California and not necessary, but they're out there, and it's good to be aware of them. There's at least one study out there that ERVs also are able to, they're not as good of ventilators because they can, through the humidity can transfer VOCs back into the house when you're trying to exhaust them. So HRVs are really the way to go in most climates in California. And pictures of balanced HRV systems. So the picture on the lower right is an HRV, and this is just kind of how the inside of the box looks. And the fresh air from outside is coming in cool. It warms up through this heat exchanger box in the middle, and it comes into the house warmer. So that's the principle of them. These systems, the downside of these are they're much more expensive to install. Of course, typical install on a single-family home would be $1,800 to $3,000 probably to install one of these. So that's why oftentimes a spot ventilation, continuous ventilation system is used. Just they're cheaper. You can get the spot ventilation, continuous ventilation fans like the Panasonic Whisper Green. One of those installed prices maybe $400. I don't know what the unit itself costs, but installed prices. I was usually installing them for about $500. Maybe get them a little cheaper. And just going to talk on economizers. Economizers are really for commercial, but just want to bring it up. You're not going to see a true economizer in most residential applications, but all an economizer is a ventilation system, and it's a ventilation system that's integrated into the HVAC system. And there are whole house ventilation systems out there that are integrated into the HVAC system, much like an economizer is. They're not called economizers though. They operate under a similar principle, I typically don't recommend integrating the ventilation system of the home into the HVAC, because the HVAC doesn't operate continuously like it would in most commercial applications. The HVAC runs almost all the time, so ventilation through it makes more sense, where in a home the HVAC doesn't operate continuously, so it's less desirable, and yeah, just not very often found. All right, so in summary, and then we'll cover some problems before we take questions. But 3 types of ventilation systems are passive or natural ventilation, spot ventilation, and spot ventilation is an acceptable method if the spot ventilation can also operate continuously. It's an acceptable method of ventilating a home under California code. And then the central ventilation system, so the balance system or the HVAC integrated system, which I said is not typically recommended, but it's out there. And then heat recovery ventilators are great for minimizing the negative energy implications of ventilation systems. And then economizers are there, typically commercial though. All right, so ventilation problems that you'll run across. So unbalanced systems, like I mentioned before, they will create uneven pressures in the building. Mainly, we don't know where the makeup air is coming from. It's always coming from somewhere. You could have a large negative pressure build up in the house, like I talked about the one house that I'd measured. But even at negative 25 pascals, that's just the pressure at which it needed to be to get enough air inside the house. So where's that air coming from? You know, around the doors, through the insulation, maybe through the attic or the crawl space, but it's leaking into the house from somewhere. So unbalanced systems are also affected often by temperature differentials, by the stack effect. Oftentimes you can decrease fan efficiency because you've got a large negative pressure in the house. And then just the infiltration. You're bringing in unconditioned air into the house in various places. So stack effect, same thing. Most homes are going to probably be no more than 2 stories, so it's not going to be a large pressure differential created by the stack effect that will have an adverse effect on your ventilation, but it will affect it in some amount. And then also just clogged systems, of course, clogged grills and holes in the ductwork. And mentioning ventilation systems, it is required and of course good practice that any exhaust ventilation systems, that exhaust air completely leave the building shell. So it's going to oftentimes, like in a bathroom, that's going to go through the roof or maybe a sidewall in the attic area. But it is required that the exhaust air leave the building completely, the envelope. So part of the BPI test is you're also, for the building analyst, you need to measure airflow. And there's qualitatively, you can do it with a smoke stick or a smoke pencil or a wizard stick, which will just basically tell you whether it's sucking out or not. Was all it will tell you. And it's really surprising how many times vent fans are installed backwards so that the air is actually blowing in instead of blowing out. That could be intentional, but I've never found one installed backwards intentionally. You can also use an anemometer that just measures airflow, measures air velocity, and then you can, through some calculations, figure out the cubic feet per minute that's leaving. A flow hood can be used, but usually in ventilation, the flow, most bathroom fans are rated at 50 CFM, and most of them operate somewhere between 25 and 30 due to the static pressure in the ductwork. So at that low of pressure, most flow hoods are not accurate that low. Flow hoods are typically for HVAC duct systems. The favorite method of measuring exhaust fan flow is using exhaust fan flow meter. It's much more accurate and quite easy too. So smoke sticks, or smoke sticks, smoke pins, smoke pencil, it's all the same thing. That's the left picture. It's a nice, small, light instrument to carry around, and it won't spill like the wizard stick on the right. Wizard sticks look really cool when you're in a house and you're showing it to the homeowner. It's very dramatic, but lots of batteries and they spill. Anemometer can also be used. Here he's measuring a supply or return in a commercial building, but it's basically it just measures air speed, and with some calculations can give you an approximation of the CFM that's leaving. And then flow hoods. Again, flow hoods are typically used to measure, the best application for them is to measure return air from an HVAC, not from ventilation systems. Specifically residential systems where the flow is low. And then the exhaust fan flow meter, or flow box, sometimes it's called. This is a simple device that can be used, and it's pretty accurate. So that's the preferred. So in summary, so the unbalanced systems, the problem is you don't know where the air the makeup air is coming from. Debris buildup in ventilation systems is going to hamper their operation, of course. And then you want to measure and just verify. Even just using a piece of toilet paper against the fan will tell you qualitatively if it's blowing the right direction and kind of how well it's working, qualitatively only. And we'll take a break there. Mike, do we have any questions?
Yep, a couple questions have come in. So the first one is a question about high MERV filters, MERV filters. The person who asked the question said that he's heard a variety of different qualitative estimations of their performance. One is that they capture and catch all kinds of diesel fumes and pollen, and alternatively, he's heard that the MERV filters are just there to protect the equipment from getting clogged with pollutants or particulates. Can you talk a little bit about high MERV filters? What are the pros and cons, and what's your opinion of them?
Sure. I guess the first comment is if you have a diesel engine in your house, you should probably get rid of it. But yeah, so it's a great question because there's a lot of debate around it. MERV is, you can't remember what it stands for, but it tells you how the higher the MERV rating, the more efficient the filter is. So the highest MERV rated filters will trap more like biological viruses and stuff if you get really high MERV. And low MERV filters, the lower the MERV, usually the cheaper too. They just stop less, so that they filter out less pollutants in the air. So and most HVACs are, ideally anyway, an HVAC is going to be designed to handle a certain MERV filter. HVACs are very sensitive to the amount of pressure buildup through static pressure in the system. So if you have a home and you want great filtration and you throw a really good filter on the HVAC, while it may stop a lot of pollutants, it's also going to increase the energy use in the entire HVAC because it creates high static pressure. So ideally your HVAC is designed to handle a level of filtration on it, and that's what it should stay at. So if your system isn't designed for a high MERV, I wouldn't spend a lot of extra money in getting a really high MERV filter because it's going to degrade the whole system's performance. The filter on the HVAC is really there mostly to keep the evaporator coil clean. It's not there so that you don't have to dust your house. So don't substitute a high MERV filter so that you don't have to dust. It's really all about keeping the evaporator coil clean. So there's no good answer of what MERV filter you should use, other than if you haven't specifically paid the guy extra when he installed your HVAC to put a big filtration system on it or a higher MERV filter, then it's not a good idea to put one on. Okay, Mike?
Yeah, great, thank you. And also, one of the other respondents let us know that it's the minimum efficiency reporting value is what MERV stands for, and it has an inverse relationship with the actual particle size that are allowed through the filter. So as you get a higher MERV value, you get a smaller particle size that's allowed through the mesh. It's kind of how it's rated.
Perfect.
The next question is about, can you talk a little bit about the distinctions between the BPI Building Analyst for multifamily versus for single family?
Sure. Let's see. So in multifamily, I guess thinking of the test anyway, the multifamily, there's no field test. There is a practical online exam that substitutes for the field test. So there's multifamily test, there's the written test, and then there's an online practical. For the BPI Analyst, there's a written test on the computer, and then there's a field-based exam where it's a 2-hour exam in a field where you basically do your test on the home. And so the proctor follows you around and makes sure you're touching on certain points on a checklist. Other than that, of course, building science is building science. So both tests check your knowledge of basic building science. The multifamily exam in general is much harder for most people. There's a lower success rate typically in multifamily exams. They just cover a lot more of the multifamily systems, chillers and cooling towers and elevator shafts and trash chutes and just the unique pieces found in multifamily systems. You do not have to take the analyst exam and then take the multifamily exam. You can take the multifamily exam by itself and never having taken another BPI exam or certification exam, but that's kind of the way they're intended, that the BPI Analyst is the entry level for most people into the field, and so that's that base knowledge. The BPI Analyst will probably get you 25 to 50% of the way toward the multifamily exam in terms of your knowledge bank. Other than that, the field exam for single family analyst, you test the ventilation systems for flow. You would do a blower door on a single-family house, and you do combustion and gas leak testing and worst-case depressurization. So that's what the field exam would look like. Those are the four kind of main components of it anyway for the building analyst. That's about all I can think of for now.
Okay, great. Yeah, I think that pretty well covers it. That's all the questions from chat, so if anybody else has any other questions to clarify what we were just talking about or anything that you're interested in, please write in by chat. But go ahead and let's keep moving along, Scott.
Okay, thank you. All right, so we'll cover cooling systems, or HVAC, refrigerant-based cooling systems anyway, and the various types, so direct expansion, variable refrigerant flow. Latent and sensible heat we'll talk about. I know we covered before, but we'll just recap on that, and evaporative coolers, just a slide. So unitary cooling systems, so this is a unitary cooling system is basically saying like a cooling system for a unit, or here the unit would be a home. Most cooling systems are direct expansion or DX systems. So like a rooftop system or a package system, it would be a type of a direct expansion system. So the picture on the top right is a package system. Often in residential, they're going to be on the roof, probably 90% of the time. Sometimes if the house is on a crawl space, it may be sitting beside the house, and then the supply duct, which is this right here, this supply duct would go underneath the house into the crawl space and then branch to each of the rooms. So that's an example of a package system. And then this one's on the ground. And then the split systems, which is probably what's found in the vast majority of residential applications. So you'd have here the picture in the left. This would be your condenser and compressor, and this piece is found outside, typically on your back porch, and then it connects to the air handler that's inside the house. Usually the air handler has integrated inside it the furnace, either gas, and so the two communicate just with the line set, the refrigerant lines going back and forth. And also it's found in some, although most homes aren't built this way anymore, but older homes you could have a room AC, or it's also called a PTAC. This one pictured here is more like a hotel PTAC than what you find in most residential, but they look just like a room AC, and it could only be a room AC, but it could also be a room AC is also called a PTAC, Package Terminal Air Conditioning System. That's what PTAC stands for. But it can also have heating elements in it, so it can either be heated electrically by electric resistance, or it could be a heat pump PTAC. So sometimes you'll see PTHP, so package terminal heat pump, and then if you've got a heat pump, then you're doing heating and cooling both in the same system. So package units are using refrigerant. Typically, again, you could have, it's possible, pretty unlikely, electric resistance as the principal heating source. Most of the time it uses refrigerant to cool and heat if it's a heat pump. And they're always going to be located outside the house, so either on the ground or on the roof. And then the split systems, that's where you've got the condenser and compressor outside the house, and they're split. So there's the piece inside the house, or maybe it's in the attic, which would be the air handler, and oftentimes the furnace, and then the other piece is split off outside the condenser. And again, it also uses refrigerant to remove heat from the house. And really, it's best to think of these cooling systems as they don't cool the house, they remove heat from the house, which is really what they're doing. They just remove the heat energy. They don't directly cool the house, they take the heat out. So the split system, again, is comprised of the inside and the outside, or the two pieces. And it can come in a lot of different configurations. Packaged terminal air conditioners, PTACs, or PTAC heat pumps, PTHPs. They're small, there's no ducts. Refrigerant is used to remove the heat again. And you could have electric resistance or a heat pump heating in the same unit. And it's usually mounted either through the wall, if it's permanently installed, or it could be window mounted. The picture just shows a bunch of variations of PTACs. And then there's also variable refrigerant flow systems. Ductless mini splits is an example of variable refrigerant flow systems. Ducted mini splits can also be ducted mini splits. And basically, the difference is they have the ability to vary the amount of refrigerant, which varies the capacity of the system. So most split systems, if you've got, let's say, a 2-ton air conditioner, each 1 ton is 12,000 BTUs of cooling, and 1 ton, the term ton comes from basically 1 ton of ice, or 2,000 pounds of ice, has the same cooling capacity. So 2 tons of ice has the same cooling capacity as a 2-ton HVAC. That's where it comes from, but a ton is defined as 12,000 BTUs. So if you have a 2-ton system and it's on in the house, it's supplying 24,000 BTUs of cooling. And that's, if it's on, it's supplying 24,000. Where if you have a variable refrigerant flow system, it could vary from 2 tons, say 24,000 BTUs, down to 12,000, maybe 6,000 BTUs, and even lower. So you can supply only the amount of cooling that's required, and instead of the big shot of cooling. And the stopping and starting on an AC system reduces the life of the HVAC or the AC system. So it's kind of comparable to city driving and highway driving. If you have the 2-ton system and it's not a variable refrigerant flow, when it turns on, it's going to cool the house really quick most of the time and then shut off, and then the house will heat back up, and it keeps cycling on and off. And that cycling on and off is that comparable to the city driving, where it increases the wear and tear on the system, where a variable refrigerant flow system can just give you the amount of cooling that's necessary, and so it stays on longer at a lower capacity, and it helps in minimizing the temperature fluctuations in the house. So it keeps people more comfortable. You don't cool the house down and then it gets hotter and then it cools back down. Now with the variable refrigerant flow, you can just kind of maintain a temperature without it cycling on and off all the time. Typically, variable refrigerant flow systems can be quite a bit more efficient than a standard constant volume system. Variable refrigerant flow SEER ratings can easily be 16, 18, 20, or more. So they're very efficient, and a lot of variable refrigerant flow systems or ductless mini splits would be set up in a manner similar to this. So you'd have one outdoor system, and then you would have here you've got 4 different zones, and each zone is its own head. So there's no ducts, but you have a different, you would have a small fan in each one of these head units that's cooling each room just the amount of cooling that each room is needed, instead of having all the rooms turn on at the same time. Maybe zone 1 and 2 is on the west side, and it's going to need more cooling than zone 3 and 4. So it's able to adjust according to the needs of each room. And then, of course, if you're not in the room, certain rooms can just be shut off, where constant volume ACs, the standard package or split systems, it's really not good to close a register and shut the door for those systems, because that, again, it increases the static pressure in the system, which is bad for the system. So you shouldn't ever close a vent in a constant volume system. It actually decreases efficiency than just leaving it on cooling a room even if you're not in it. So that's the advantage of variable refrigerant flow systems. Let's take a break here and see if there's any questions before we move on from these systems.
Sure. So there's one question more about the program processing side. There was a student who's asking about the first class. So just to reiterate, for everybody's benefit, all of these classes are being recorded, and they are all posted on our YouTube page. Probably the fastest way for you to get there is to search in Google or your other preferred search mechanism to search for the Multifamily Upgrade Program YouTube page, and you'll find it there. Alternatively, you can go to multifamilyupgrade.com and look for the link to our YouTube page. But all of these trainings and trainings from our other series are available online and on demand. And just a comment that the MERV question becomes much more difficult when dealing with multifamily buildings. And I think that's probably a common feeling, but I wondered if you wanted to comment on that, Scott, the difference between single family and multifamily in terms of the complexity of picking the right filter and managing the right balance of pressures and all that.
Well, I guess most multifamily properties, they're still going to have unitary cooling systems, the cooling system types we've just talked about. So it's, you know, that filter is just going to be filtering the air in that one unit. So each unit would have its own filter and its own complete system. So ideally, the systems are designed for a certain MERV, and maybe for that reason, multifamily could potentially be easier because they're all going to be designed for the same MERV filter, and your multifamily property owner hopefully is going to be changing those filters themselves so that they can always get the right one in the unit. So I guess conversely, maybe picking the right MERV is even easier in a multifamily unless there's something that the person was asking about specifically that I'm not aware of.
No, just a comment, but we're happy to get more feedback and details if needed for the person who's been asking about MERV. So feel free to clarify and ask again if you'd like to. But that's all the questions that have come in, Scott. So why don't we go ahead and move forward?
Okay, sounds good. All right, so just to review, cooling systems, refrigerant-based cooling systems, all work off of refrigerant, and the principle of the refrigerant, how it works is the principles of latent heat and sensible heat, and I know we've talked about it before a little bit. Just to review, though, latent heat changes the state. So in a HVAC system, when, let's say we have a split system, when the refrigerant makes it into the air handler, it's going to be a liquid. The air blows across it, and as the air blows across it, it's going to change the state from a liquid into a gas inside the air handler. And that changing of state is about latent heat, and it allows more cooling than just taking, than say, like if you just take cold water into the house and blow air across it and you leave with a slightly warmer water. Refrigerant is much more efficient at that because you're able to, the refrigerant is able to absorb more energy because of that latent heat element. And then the sensible heat is really more about the temperature you feel in the house itself. And if you set your thermostat at 76, that's really a measurement of sensible heat and not the latent heat. And then just how the system works, again, sensible heat is the diagonal line where as you add heat, the temperature increases until you get to that, till you get, so the liquid refrigerant making it to the air handler is going to be at a constant temperature through the process, while you're in that latent stage where you've got both liquid and gas until you leave the air handler. And by the time you leave the air handler, all that gas should be now a vapor, and that gas temperature will rise until it goes out to the condenser and compresses. And then you're going to compress it. It's a change of pressure, but it's also it's removing heat from the air outside. So think of it as a sponge where the refrigerant absorbs heat inside the air handler, takes it outside, and the condenser squeezes that sponge and squeezes the heat out to the outside. That's kind of how it's working. And then just one slide on the evap coolers. You find them in residential, not all that often, but in some older existing buildings you're going to find them, and typically it uses 100% of the outside air. It uses it blows the air across the moist wick, and that it lowers the temperature, and that's also, it's using some of the same principles of latent heat in that case, and then it blows it in. So it's using water to help cool the air before it enters the building. Obviously, it's pretty efficient. There's really only a pump and a fan energy happening here. Just not found all that often in existing residential anymore. So the three main types of unitary refrigerant-based systems are going to be a split DX. DX is direct expansion, a packaged DX, and then PTACs, and even PTACs have direct expansion valves in them. And cooling systems, they just move sensible heat, and then swamp coolers are typically 100% outside air, and they're very efficient. A little bit on maintenance of the cooling systems. The big maintenance items are going to be P-traps, and then the condenser and the evap coils, air filters, which we've already touched on, and the blower motors. And for the P-trap, there's a picture of the fanciest P-trap I've ever seen. But the P-trap is there. It's found near the evaporator coil, which is part of the air handler. And why it exists is the air from the home blows across the evaporator coil and heat is being removed from it. Well, while the heat is being removed from it, moisture from the air in the house condenses on that evaporator coil. That evaporator coil is your can of soda sitting out, and where the dew collects on your can of soda, exact same thing is happening in your evaporator coil. So here, when that dew collects on your evaporator coil, it's going to drain to the bottom and then leave by way of the P-trap. And the P-trap, is just what you see there, but the low portion should be full of water, and that blocks air from escaping from the evaporator coil. So it helps stop air leaks through the evap coil is part of the reason why we have a P-trap at all. And it would be also, if any debris were to come in, that's where it would stop, so it's easier to clean out. So you just want to make sure they're clean. Most systems have a backup system that will not have a P-trap on it. So if the P-trap plugs, or any part of that line plugs, it'll come out of the backup system. And where that black plug is on the picture, this would be, and it could be on another side for this one, but this could be where the backup system was. And the backup system is a little bit higher than the one with this P-traps associated with. So all the water should be draining out of this P-trap system, and then anything else will come out of the overflow. And that overflow will drain, usually it drips over a window. So if you see water dripping from above your window, it usually means the primary system is plugged. And the main problem with plugging the primary system is what happens when the secondary system plugs is now you're going to have water overflowing. And if your system's in the attic, it's going to be overflowing onto your ceiling. So that's why you've got the two systems. And then you want to, of course, clean condensing coils. You want to, the one on the left, I don't know how it could possibly get that dirty, but sometimes dryer vents are close and that can plug it. But you just want to, usually a garden hose is enough to clean them out once every year or two. And that's the condenser coil, that's the piece outside. And then the evaporator coil is this piece that's found in the air handler. And again, if this is a package system, the evap coil and the condenser coil are all in the same package. But this is showing a split system. So keeping the evaporator coil clean is also important. The evap coil gets dirty because, like your soda can, where dew condenses on your soda can, where the P-trap takes the condensate out, here the soda can or your evap coil is going to be wet. So any dust or dirt that's going to flow through the system is going to stick because the coils are going to be wet most of the time. So it's why they're going to plug even faster than like an outdoor unit. And this is why you want a good filter on. You never want to run your system without a filter, because as you plug up this evap coil, it increases static pressure in your system and decreases the efficiency of your system, and it's going to shorten the lifespan of your system as well. So, the higher the MERV filter, it's going to keep the evap coil even cleaner. But like I said, systems are designed for a certain rating, and the static pressure is very important. Evap coils should be cleaned periodically, just so that they don't look like the one on the left. You hire the guy on the right to keep it clean. And then, filters come in a variety of different types. Most of the ones are disposable. You pull it out and you throw it away, right? Some are going to be, you can clean them with a hose, and we've already talked a lot about MERV filters, so won't talk any more about them. And of course, if you have animals, you should change your filters more often, because there's just going to be a lot more hair in those filters. And children, especially if you have hairy children, could be a problem. But I think that's on there just to help. I think that's mostly talking about air quality for the children, but pets for sure. If you live in a dirty environment, for sure you want to change it more often. When I would replace HVACs, I would usually leave a stack of filters in the house with the date on them, saying, basically with the date saying January 2016. So if my homeowner sees and it's February, he knows that one needs to go in. But recommend at least twice a year, beginning of the heating season, the beginning of the cooling season. 4 times a year is even better. And then, but it's also going to depend on when you change it, how dirty it is. You may have to increase the amount of time, or how often it's changed. And then the other piece of the blower motor of the HVAC system is the blower motor, and this is what a typical blower motor looks like. It's called a squirrel cage, and the filter is upstream of this, so the filter should stop all this debris from getting into the blower motor, but you want to make sure the blower motor stays clean as well. That's usually a little easier to clean, but you want to keep that clean as well when you're doing your standard maintenance. And then in summary, just keep things clean. Keep the P-trap clean, the condenser and evap coils clean, and change your filters often. And that's it for today, and we'll take some questions if we have any.
Yeah. So there's a question in here that's sort of for you, Scott, about general BPI qualifications and certification. If a student were to take the classes within this series of trainings by web, would they have to later go into a classroom in order to be eligible to take the qualifying exam for BPI single family?
No, they do not. It's not required that you sit in any classroom training to take any of the BPI exams. These webinars are enough to qualify you, but in reality, you don't even need to sit through these. If you're good at self-studying, you can just study yourself, and when you're ready, contact a proctor, such as myself, or one of the test centers. They can be found on the website, and they can make sure you get tested.
Great. This one's a little bit more technical in nature. Why are evap coolers not installed very much anymore if they are really so efficient?
Well, I'm trying to think of how to say it politically, but I think a lot of people don't like the inconvenience of swamp coolers, because if you're going to operate a swamp cooler, part of that, you're bringing in 100% outside air. So that means you have to open up all the exterior windows to let that air out. And I always assumed the homeowner was an idiot when I worked on a home, and in that, I guess I'm saying, like, trying to make things idiot-proof, right? So that it can't be messed up, and that's it also goes for whole house fans, right? Whole house fans are very efficient, and they are actually part of the code now. But it requires the homeowner to operate the home and open windows and close windows, and that's kind of taxing for some people. So majority of the time, people don't want that much work in their comfort, so they would prefer to just turn it on, flip the switch, and they know it's going to operate appropriately. So I think that's probably why they're not used anymore. But yeah, they are incredibly efficient for sure.
Okay, another question. The question is about requesting a local referral in Sacramento. So, Scott, can you comment generally on partnership and teaming and how that kind of works in the home performance world, and is partnership between, for example, an HVAC contractor and an energy consultant, beneficial in your experience, and is that widely used tactic when trying to win work and implement and work on projects?
Yeah, it's a good question. And so I've done it in various ways. I've worked for an HVAC company in Sacramento that and tried to make the home performance part of the system install piece, because and really that's the right time. If you're installing an HVAC in a house, it's the #1 largest dollar purchase you're going to make that's going to affect the energy use of the home. So getting it right is really important. And so before you put it in, do the air sealing, do the duct sealing, maybe add insulation, do all those things at once. Makes a lot of sense. So it's a great way if the HVAC company has a building science department. It's one way to go about it. The downside that I found is most HVAC companies that I know, and the one that I worked for, they're into changing HVACs. That's how they make their money, and they would like to sell the homeowner the job one day and install it the next day and get paid on day 2 of the job. It's just turning, it's making money. That's their business model for most of them. If you introduce building science with it, and now you're doing a blower door and a duct plaster and you're adding insulation, well, they're not used to all that, but it turns a 2-day job into, it could be a 2-week or a month-long job, and so it slows their whole sales cycle process. So I didn't last very long there. It just wasn't a good fit with their business model. I've also done it where I've worked for a GC, and I partnered with an HVAC person who was very knowledgeable in BPI, so he understood the bigger picture. And so then I would take my clients as a GC who were interested in building science, and I would bring him in and he understood it, and I think mainly because they were my clients instead of his, he was okay with a slower process. He typically made more money on my jobs than he did his own because of everything else that was happening. He was just able to make more money on it because of all the added value that we were bringing. But it was that was probably the best method I found to do it. But if in terms of referral, if you're looking, I think if you're looking for a home performance contractor, at least, probably the best way to find one is go to the local utility and get a list, because pretty much every local utility is going to have a list of participating contractors, and call the people on the list and find who you like to work with. That would be my suggestion. That's it.
Okay, let's take one last question, and then we'll call it. So the last question here is a question deep in the weeds, which is good, on the ACCA, that's ACCA Manual J, D, and S. Officially, it's law, but according to one of the practitioners on the phone, it's not widely incorporated or implemented. Do you have any suggestions or resources for expensive and fairly accurate? The question says over-the-counter JDS, but I believe what he's trying to get at is how do you efficiently and inexpensively implement the requirements of the ACC Manual JD and S?
Well, yeah, that's a good. It's another good question, and again, it takes time. So the typical HVAC contractor, if you've got a 2-ton system, they're going to sell you a 2-ton system because that's the quick thing. Unfortunately, the home was probably never sized to begin with. So if it had a 2-ton, it wasn't actually properly sized to begin with. So it could be under, but most likely it's oversized, as most systems are. Plus, even if you're replacing a 2-ton system that was installed in 1980 with one today, it's just going to be so much more efficient. So that, with increased efficiency, you would need a smaller system. So sizing is very important, let alone the fact that you change windows, you change insulation. All those mean you would need a smaller system. But in terms of doing it efficiently, I mean, we do it in EnergyPro. We do it all the time in EnergyPro. It still adds time to the whole process. If you really want to turn it quick, turn the job quick, sell it one day and install it the next day, I don't know how you get you do ACA manual JD and S, and just so people who don't know, ACA manual J is equipment sizing, so it tells you how much. So do you need a 2-ton or a 3-ton system? Manual D is duct sizing, and manual S then helps you use systems to helps you pinpoint which system should meet the requirements of J and D for the home. But I don't know of any shortcut systems. I know that Train makes a version of the software. RightSoft, of course, is the typical industry benchmark for using for JD and S. EnergyPro works just fine as well, but there's no shortcuts that I know of other than modeling the house in some type of software.
Great, yeah, thanks for getting into that. And from my perspective, as working on kind of the program side, we often see the, as Scott was saying, kind of the one-for-one, like-for-like change-out. And that's often not the case, but it's a tricky sell to try and incentivize any HVAC contractor or influence any HVAC contractor to actually do the legwork to right-size the equipment. Because ultimately the liability or the complaints are going to be on the contractor, as opposed to the the energy benefit is much less important, let's say, oftentimes in the single-family world than the comfort that the tenant or the homeowner feels from a correct HVAC system that they perceive to be working more effectively, because typically the bigger systems will just cool them off faster. But that gets into a whole other bag of worms. So let's leave it there, and I will just say thank you everyone for attending. As I mentioned before, all of these recordings are available on our YouTube page. Thanks for the great questions throughout, and Scott, thanks for the great information. Would you like to go ahead and have the last word, and I'll stop the recording thereafter?
I just want to say thanks for everyone attending and the questions, and we'll be back in a couple weeks with continuation of HVAC, a little pressure, and some water heating.